So now on to the main event. Our speaker tonight is Ken Stedman. It wasn't that long ago that Ken's dad, Don, was standing in this very spot telling us about this cool device that he invented that would measure the car emissions in real time as they drove past a spot in the road. He had this device aimed at the tailpipe, and he could tell what was coming out. And he knew, long before the feds did, that Volkswagen was cheating on their exhausts. It was really cool. Well, Ken has inherited his father's inventiveness, and we're going to find out about that tonight. He began his career as a chemical engineer. He got a BS in chemical engineering at Stanford in 1987, and he worked in the pharmaceutical industry for a few years, but eventually he was lured into molecular biology, went to Berkeley, got his PhD there, and he did, as near as I can tell, 4 different postdocs. And it was the 4th one that turned him on to weird viruses. Viruses that can survive in places where really nothing should, like the inside of a volcano. And Ken has specialized in this area ever since. He came to Portland State in 2001, been here ever since. He's pulled in close to $5 million in funding and published almost 40 papers. He was the co-founder of the Center for Life in Extreme Environments and was in great demand the past several years when COVID hit as an expert to explain virus biology on various national news programs. He's won numerous awards. I won't list them all. My favorite is that he was a finalist for the Golden Mole Award for Accidental Brilliance on National Public Radio. Curious to know what that meant. Maybe he'll tell us. Of special interest to us tonight is a company that he founded in 2014, Stone Stable. And he'll be explaining, I think, some of the chemistry and biology behind that work.
Let me get myself wired up here. So actually, it was only 3 postdocs, and it was the first one, actually, that got me excited about these kinds of weird, crazy viruses. So I need to talk to Dave a little bit about getting those facts straight. I did also need to mention that one of the reasons that Dave knows about me and what I do is that I took his scientific glass blowing course, which was awesome. It was so much fun. My condenser wasn't completely airtight, but that's a bit of a different story. So a lot of that actually has to do with the viruses under glass process here as well. So first, thanks for the invitation. Nice turnout, and hi to all those people on video. Hopefully we're all on the same screen here. So I'm going to tell you a little bit of a story, and that story is really about how this company came to be, and it's the reason we got the Golden Mole Award for Accidental Brilliance. And if I have a real quick aside here for my joke relative to my late father, they had this competition at National Public Radio about, things you never thought were going to turn into anything interesting, basically. And I was like, yeah, this doesn't sound that interesting. And then my dad said, you need to apply for this. What you're doing is exactly what they're looking for. Well, okay, fine, if I have to. Did what my dad told me to do as a good son. And then lo and behold, we ended up being one of the finalists, which was also great fun. And I also found out about it when Kiki Sanford, I don't know, maybe you know Kiki Sanford, This Week in Science was a podcast. She actually comes as a seminar speaker at Portland State. And I'd just gotten the message from my dad that they had contacted him to say that he was one of the finalists. But they made a mistake. They actually meant me. So my dad sending me an email saying, I think they want to talk to you, but you shouldn't tell anybody. And then Kiki Sanford, who probably has an audience of multiple tens of
said, I just heard about this that I got finalist in this national public radio thing about accidental brilliance, but don't tell anybody. So that's a process. But I will tell you actually a little bit about that whole process, because it was really serendipitous that we came to this whole process. So I'm part of Florida State University Center for Life in Extreme Environments, and more recently the Extreme Virus Lab, and the X, of course, is a really important part of the Extreme Virus Lab. Full disclosure, Stone Stable is a company that I started in 2014, which is really trying to commercialize a lot of the technology I'm going to be telling you about. But before we get there, I need to give you a little bit of background. Usually the title of my talks is Viruses from Hell. That's what Dave was talking about before. Literally, viruses from environments that things shouldn't be living in. This is a picture from Sept Volcanic National Park from 20 years ago, when I first started sampling there, right near to a place called Bumpus Hell. And the reason it's called Bumpus Hell is that a certain Mr. Bumpus in the late 1800s was taking some tourists around, fell through the snow into some of the hot springs, and lost both of his legs. So that's the reason it's hell. They're really not very nice environments for us. But it turns out they're great environments for viruses. And one of the main viruses we work with, is anyone here read Japanese? That's probably a good thing, because I probably got it wrong. This, I believe, is Jigoku virus. And Jigoku is translated as hell. And this particular location is Chinoike Jigoku, which is in Beppu, in southernmost main island of Japan, in Kyushu. This really does look like tomato soup. The sign that you can sort of barely see the back here, so I can corner over here. Which way around this is? Doesn't really matter. The sign at the top there says 70 degrees Celsius, pH 3. So pretty nasty conditions for most of us, but really wonderful conditions for the viruses that I've been working on for 20 odd years. So why am I working on these viruses? Who cares, right? Why should you be interested in looking at these things? Well, mostly I got interested in these because I got really excited about archaea. How many of you know about archaea? You know about archaea? You know about archaea? Any of you don't know about archaea? So archaea are a whole completely different group of organisms from bacteria or eukaryotes, which may or may not be closely related to the common ancestor. The more we think about it, actually, probably more of the common ancestor of us. So we're more closely related to archaea than bacteria are to either us or the archaea. And there's some pretty good evidence for that. But I get interested in these because these are the organisms that live in these crazy environments. So I said, okay, I'm really interested in looking at these. And I'm interested in how they can survive it. How can something survive in boiling acid? Biology usually, again, poor Mr. Bumpus, he lost his legs, right, when he fell into this environment. So how can you survive under these kinds of conditions? So I got really interested in studying this. We particularly studied a set of organisms called Sulfolobus, actually renamed to Sacrolobus, optimal growth conditions, a near 80 degrees Celsius, and a pH of 3. So they love those kinds of conditions. How they deal with it, we really don't know. Molecularly speaking, we're way back over here on this insignificant little branch in the tree away from the other side. But what do these environments actually look like? This is a volcanic hot spring. Actually more of a mud hot in Sept Volcanic National Park. This was from a couple of years ago, but we were just there 2 weeks ago. And it basically looks about the same. This particular spring is 90 plus degrees Celsius, which is actually boiling at this altitude. A lot of outgassing. The pH here is 2. Just a little bit too hot, a little bit too acidic for our favorite organisms. One of the things people always ask us is, how do you collect a sample there? The answer is a very long pole. And this is a few undergraduates from Florida State out there collecting samples from this environment, and then we bring those back to the lab and see if we can find some viruses. And this is where some of the real first, great sort of, I don't know what the right term would be, but epiphanies were that the viruses that you find in here don't look like any virus I've ever seen before. Very, very strange. This is getting my first postdoc where I learned about these things. They look completely different than any other kind of virus. And the whole talk that I'm not going to give this evening is about those viruses over there on the right-hand side. SSD1, fascinating systems, spiral viruses, fluzellos, completely different in terms of their structure than any other virus. I'm not going to talk about those because I've got other things I want to talk about. One of my favorites are actually these guys. These are viruses that have a structure that looks like literally a champagne bottle. These bars, actually I don't know if there's a scale bar in here. The scale bars here are about 100 nanometers. So really, really small sugar. You have to break up a lot of these in order to get a whole bunch. But just really fascinating structure. And we have very light idea on how all of these things fit together. But there are a few viruses in these conditions that look a little bit like viruses that you find in other environments, particularly this one right here, which I must admit I'm somewhat proud of because I'm the first person in the world who ever saw it. It came from a spring very close to this location right here. Slightly less gray here. Yes, this was 22 years ago. Collecting in Yellowstone National Park. This particular spring actually not unlike the Chinolite jigoku. Oh, I forgot to say what Chinolite stands for. Anybody know what Chinolite stands for? Blood pond. So blood pond hell. So this is actually pretty close to that blood pond hell. Sample where I remember this, I found this virus and I was looking at the electron microscope, and at first I was looking for these nice lemon-shaped things, and then I saw this. I was like, must be contamination, right? Can't be something like this. This looks too much like a normal virus. Well, long story short, it actually was a brand new virus. As you hear about these things, at T equals 31, a constitutively symmetric particle. I don't see very many people who are interested in that. But it's got this icosahedral symmetry. And icosahedral symmetry turns out to be very, very common in viruses. Because if you think about it geometrically, how do you make a structure which has maximum volume and smallest surface area? You want to make a sphere, right? But how do you make a sphere with repeating protein subunits? Really hard. However, if you have icosahedral symmetry, you can get pretty darn close. And so it turns out that icosahedral symmetry is something that's incredibly well conserved across all kinds of different viruses. Some coronaviruses, not the one that we're particularly caring about right now. So I was pretty excited about this virus, discovered it, we got a PNAS paper out of it, and really neat structures coming out here at the five-fold axis of symmetry. But then our collaborators, Liang Tang and Jack Johnson, said, oh, yeah, those things are really interesting. But what's much more interesting is how these things fit together. And getting back to that spherical process, you've got to have lots of repeating subunits that come together to make this particular structure. So they looked at this particular structure, and what they found was really kind of amazing. The first one, STIV, sulfurous turreted icosahedral virus, I didn't get to name it, very boring name. But the main subunit, how you put all this thing together, has a particular structure to it, again, not terribly surprising. But it turns out that structure is almost identical to a virus that infects bacteria and to adenovirus that infects us. And these are completely different kinds of organisms. I showed you back in the beginning, I told you about archaea being more closely related to eukaryotes than the bacteria, but these viruses have basically identical structures. They're major capsid proteins. But they have zero sequence similarity. So how do you explain something like this? Well, there are lots of different explanations. In terms of not having a time machine, we don't know how to tell. But one possibility is that there was what we call horizontal gene transfer. So a bacterial gene went to an archaea, which went to a eukaryote. We think that's unlikely. Convergent evolution, this is only one of the ways we'll make these kind of structures, but I showed you all these really crazy structures before, so clearly it's not the only thing. So we think this is evidence that there's a common ancestor of all these viruses that infect bacteria, archaea, and eukaryote. Well, we got this published, PNAS, and another paper that got published on this. But this brought us to a really interesting conclusion, and that was that if there's one kind of virus structural protein that has a common ancestor, it must have infected the common ancestor of bacteria, archaea, and eukaryote. And most estimations now are that's between 2.5 and 3 billion years ago, which is very, very long time ago. So this brought us to a very interesting question. just see virus particles.
I think the oldest rock that has some kind of virus is about 600 million years, these stromatolites.
So those stromatolites, those have bacteria in them. And there are some cherts back to about 3.5 or 3.8 billion years old that pretty clearly have bacteria in them. But nothing clearly viruses. The technology to actually see viruses was the electron microscope developed in the 1930s. So not billions of years ago. We've known about viral disease for thousands of years. But if we're right, and we think that this virus structure was infecting these things billions of years ago, there should be a bunch of viruses in rocks. So how do we find them? So this brings us to Dr. Jim Laidler, who was actually Dr. Jim Laidler before he started his PhD at my came to my virology course. I'm going to do a quick plug for Portland State. Sat in front of my virology course, knew more than I did for most of the questions that were asked in the course. Came into my office one day and said, Dr. Stedman, I have this confession to make. I'm an anesthesiologist having a midlife crisis. I'm going to get a PhD with you. And I said, ow, 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 ow. So somehow I convinced Jim, or Dr. J, as we called him, to work on this particular project was to see if there are virus fossils. Viruses in rocks, like exactly what you were pointing out before. So where are we going to look? Well, the first place to look is in the place that we're already looking for viruses. Hot springs. How many have been to Yellowstone? Mammoth Hot Springs, the amazing terraces, all of this minerals. And where do those minerals come from? They're leached from the rock at depth, at high temperature. They get to the surface, they cool down. What happens if you have a cooling solution that's a bunch of minerals in it? It precipitates. And what does it precipitate on? Precipitate on whatever's there. In this case, the trees, which are there, but we're interested in the viruses, right? So presumably, you should be getting precipitation happening on the viruses in these particular hot springs. So we did this. I'm sure all of you read astrobiology. You actually might read astrobiology. But published this in 2010. And what we saw was we actually did get this mineralized coating on a number of different viruses. But let me tell you a little bit more about this particular story. This is really mostly Jim's work. We decided to work with bacteriophage T4. A couple of reasons to work with bacteriophage T4. It's a bacterial virus, of the T-Rex of bacterial viruses, but it has this amazing shape, it's actually relatively big and easy to see in the electron microscope. If you just look at non-treated bacteriophage T4, this is what it looks like in the electron microscope. And if you treat it with silica, we decided to use silica for a number of different reasons that I'm happy to get into a little bit later if people are interested, just to look at what's happening in this precipitation process. It's easier to look at in this particular slide. Up on the upper right-hand side here, you see the T4 that's coated in silica. On the lower left here, it's my left, your right, is untreated. So really clearly there's a difference between silica-treated and untreated viruses. We wanted to show that this is actually the case. We did some EM work also at PSU with a wonderful electron microscope that unfortunately was just sold. Looking, maybe you want your electron microscope, I don't know. So OL analysis really clearly showed that you've got silica coating that happens on these viruses under these simulated hot spring environments. So, great stuff. Only one problem, and that is, if you leave the viruses in these high mineral conditions for very long, they become these unrecognizable blobs. And unfortunately, there are lots of unrecognizable blobs in really old rocks. So we don't actually know whether there are lots of virus fossils. We're working with people trying to develop more advanced electron microscopy techniques to figure out exactly what's going on in this process. But at this point, we got that paper, great. And then Jim said, well, what happens to a virus once this happens to it? Not surprisingly, it stops being infectious, right? So if you look at bacteriophage T4, over a couple of days under these high silica conditions, it loses its infectivity. It's a log scale on the y-axis there, 1,000 to 10,000 fold. Interestingly, if you look at a virus that you normally find in these hot springs, it's resistant to getting coated in these minerals because it's evolved to be under these high mineral kinds of conditions. So that's exactly what we expected. We also looked at a human virus, in this case the vaccinia virus, the smallpox vaccine. That gets inactivated really quickly. But curiously enough, there's some viruses that don't get inactivated at all. Now, all of you notice here there's something weird going on this right-hand side of the graph here. Well, this is where the accidental brilliance things comes in. As I told you, Jim, anesthesiologist, doing a PhD with me, actually slightly older than me, had to go home with his kids. So he's right in the middle of setting up an experiment to say, okay, we're losing our infectivity here. But to test the infectivity, you've got to do separate assays and solutions and so on and so forth. And he had to go home with his kids, right in the middle of that experiment. He came back the next day, and lo and behold, the viruses started to get their infectivity back. So, for a long time, we actually called this the zombie virus experiment. So, all kinds of fun, kind of Dawn of the Dead viruses, etc. But what happens is that inactivation process with mineralization is reversible, and you get the activity back. Which is really cool, great, interesting, we wrote a paper about it. But who cares about bacteriophage? If you're a bacteria, bacteriophage are very important things. They're the most abundant viruses on the planet. But Jim, being an anesthesiologist, said, well, there's actually a number of viruses that people actually really do care about becoming inactive and reactive, particularly vaccines. And when you have a vaccine, you need to get it from where you produce it to where it needs to be. And most of the time, you have what's called the cold chain. So logistics, you've got to get that particular vaccine from when it's being produced to actually getting into somebody at a temperature range between 4 and 8 degrees Celsius, which is okay in the developed world, but really hard in the developing world. So we said, well, what happens now if you take these mineralized viruses and instead mineralize vaccines? So together with Keith Badgett at the Providence Cancer Center, we did some experiments where we took silica-treated vaccinia, now expressing epitope outside, and basically showed you can take this silica-treated virus, inject it straight into mice, and you get the equivalent immune response, T-cell mediated immunity, and I can talk about details here. And so this was really exciting because it means that that silica coating is coming off inside the animal once you put it in, and you're getting an equivalent immune response. One of the things I didn't show you is when you've done this coating, it keeps those viruses stable for months under drying conditions. So we wrote a patent. We got actually now 15 different patents in different parts of the world. We got some NIH funding. We decided instead of doing injection with vaccinia, we'll do silica-coated flu virus because this was pre-pandemic, and now this is the flu mist, so the intranasal vaccine. We say basically it's the equivalent thing. So you take silica-treated virus, you put it in the nose of a mouse, which is not completely straightforward, and you still get a nice immune response. So this was really the genesis of Stone Stable, and then of course this happened, as all of us are now completely aware. So the company decided, okay, well, flu is all well and good, vaccine is all well and good, but we really need to do something about the pandemic. So what we did is we said, we'll now try and look at now doing mineralization, and specifically silica, of some of the coronavirus vaccines. And we specifically started with the adenovirus-based, the Johnson & Johnson, the AstraZeneca-based vaccines. Treated them with silica and then said, what happens? Are they stable or are they not stable? And so just as a pictorial way of looking at this, on the left-hand side from your point of view, at the top is untreated vaccine-like. In this case, it's got a green fluorescent protein gene, so cells glow green. If you've actually gotten cells that have been infected by this particular virus, if you freeze that particular vaccine, then you completely lose infectivity. If, however, you now do a silica treatment on the right-hand side, you get way more of the cells that are glowing green, so you're getting much better transfer of this particular gene. And with a freeze thaw, you don't completely kill the process, but it's still definitely getting some kind of response here. Now, it's a pretty picture. We've actually done now some quantitation of this, flow cytometry, but basically the dots at the bottom in that big sort of column part, those are the uninfected cells that are not glowing green, and everything's above that are the ones that are glowing green. On the left-hand side, we have no silica. On the right-hand side, silica. Pretty obviously a lot of dots up there. You quantify this. All of these high bars here are in the presence of silica. Do 2 rounds of freeze-thaw. The small amount of infectivity that we have in terms of the non-treated basically goes away. That still looks great in terms of how we're getting gene transfer here. So you may all be asking, why the heck is he talking about this stuff in an ACS? Well, because how do you do this process? How do you get silica on there? We've actually done 2 different processes for this. One, which is one that was developed by Jim, which is basically taking advantage of the fact that sodium metasilicate solutions are really metastable, and it depends on what pH they're at. So if you just make a sodium metasilicate solution, which is dirt cheap, well, dirt cheap because silica is actually rock, so it's not surprising. You just make a solution that is a pH 13. It's really stable at pH 13, but pH 13 is not really good for most viruses or most anything. But if you adjust the pH to 7, then it starts to precipitate. And it's going to precipitate on whatever is in whatever you have. So if you have viruses in there, it's going to start to precipitate on those viruses. And so those are the very first experiments we did. Turns out this takes quite a long time. I think it's more scalable, and I'd love to talk to people about who have some experience with process engineering, what works best for that. But we've also done sol gel chemistry for this process, pretty classic, mixing together some usually tetramethylsilanes and do hydrolysis, and then those start to combine with each other, and you end up making basically a gel around whatever you're looking at. We get similar kinds of results. Either way we do this, our patents are actually for both of these. This is actually an area where we could really use some help. So this is one of the reasons I actually agreed to come and give this talk, is if anybody knows good silica chemists, we could really use some help here at Sept. So, overview of what I just mentioned. I probably haven't taken my full time, but I'm sure no one's going to complain if I do. So, what do? We take an unstable vaccine, we coat it in silica, that stabilizes it, and then all you need to do is take that stabilized vaccine, put it into, hopefully, a patient, becomes active, and people become now resistant to whatever original thing that they started with. So, how do we start? Zombie viruses. How old are viruses? Virus fossils. There probably are a ton of them, but we don't really have a good way of detecting them. And through accidental brilliance, which is why we got that NPR award, we think we figured out a way to stabilize vaccines and hopefully really save the world in that process. You can reach me at Fort State with the PDX email. If you know somebody who's a good silica chemist who's looking for a job, please get them to send an email to ken@stable.com. And if you like and you want to hear way too much about how cool vaccines are or bike commuting, you can feel free to follow me on Twitter. So thank you for your attention. Thanks for the invitation. And I will do my best to answer your questions. I make no guarantees. If you know. Yeah.
You mentioned living virus, but a virus doesn't live by itself.
So this gets to a question that I think we were talking about a little bit earlier, is are viruses alive? And my standard answer to that question is to obfuscate and not answer the question. I say viruses are part of life. Life as we know it on this planet will probably not exist exist without viruses. And those people in this room who know that they are, who take my virology class, know that 8% of our genome is viral. And probably true for most other organisms. A lot of the evolution that has happened in order to get us to who we are is dependent on all of these viral interactions. So, but avoiding that point.
So the next question, these viruses that survive in these hot conditions, where do they multiply?
Where do they multiply? So the question is basically, given the viruses in these extreme conditions, and they're surviving in these extreme conditions, whether they're alive or not, we can argue about that later, how are they making more virus? So they're actually infecting things that also live in those extreme environments. And those are the archaea that I mentioned really back at the beginning, sacrolobus. But understanding that virus-host interaction, because getting back to your point about is a virus alive? Well, the only way a virus can be alive and make more of itself is it infects something else, a host. And so the hosts there, those are all going to be, in the cases of the extreme viruses in the beginning. Now, these viruses, the ones that we've zombified, they're not infecting anything because there's nothing for them to be infected at that point. Yeah?
So the viruses that are you find in the hot springs, you hinted a little bit about were they originally in something living that fell into the hot spring and they adapted? I mean, is there any history to that?
So I'm going to paraphrase your question because I'm not sure quite how to answer it. But this is those students out there. Best thing to do if somebody asks you a question you don't know how to answer, rephrase it and say, "Okay, question you do know how to answer."
That's why I asked that.
Yeah. So I think what you're asking about is basically how do the viruses and the organisms in these hot springs get there in the first place?
Yeah.
And then how have they evolved in that place for as long as that hot spring has been there? Or is it something which has come into it and then evolved in place? And so the answer is we don't know. Also a great answer, by the way, to lots of questions. But it does appear that certainly a lot of organisms, if you look back at some of the common ancestors, may have be an artifact of how you build some of these phylogenies, how things are related to each other. Many of them seem to be thermophiles, and so a lot of people think that life arose in a high temperature environment. And there are arguments for that and arguments against that, chemical, physical, genetic, etc. But one of the reasons they're called archaea is for old. And so people think that they may have been there for a long period of time. Unfortunately, as you probably know, a lot of these hot springs are pretty ephemeral.
Right.
And so how do they get from one place to another? Maybe if they're coated in silica, they can get from one place to another. And what happens in volcanoes, what happened in Mount St. Helens, exactly. You have these massive volcanic eruptions, and that dust spreads throughout the world. So my students at one point said, Ken, we should set up an experiment on the roof. We should put some culture media out there and see if anything falls in it. And I said, that's a crazy idea. Maybe not so crazy after all. We still haven't done the experiment, but just thinking that.
Well, you know that they're going to do that.
Yeah. Well, and we're talking geologic time scales here. So yeah, there's yes, I've been at PSU for a long time, but not now. Yeah, that's right.
Actually, following up on that point, the mineralization is not necessarily silicon, but other mineralizations. Correct me if I'm wrong, but isn't there a chance that these things could be ejected from our planet and travel interstellarly? And I know there is issues with people with astrobiology bring up that maybe some of this stuff gets transferred. We know the conditions are right for making amino acids on comets and some other complicated things. So how stable to harsh conditions are these things really going to be?
Right. So, yeah, Troy basically asked how stable are these things once they get put in silica, and this is the grant proposal that I've written like 3 times and it's never got funded. At least with these conditions, with the silica that we're doing, it's up to a couple of months. And even in the most optimal situation, if you think about like transit from Mars to Earth, for instance, we're talking much, much, much longer time scales than that. So it seems unlikely. That being said, we haven't looked at all of the details of this.
So obviously in space, the major concern is radiation. So, for example, making molybdenate clusters, which are very big, very massive, very good at absorbing radiation, and they do naturally form, maybe something like that. So better thing for a long term.
Again, so the point is maybe molybdenate or something like that, some other kinds of minerals for clusters. Fabulous ideas. We're still trying to get funding to do some of those experiments. Although one of my colleagues at the European Space Agency, who's actually in a number of different viruses now, not just these kinds of viruses, but also how stable are they to the space environment, and just literally space environment. So going up ISS and having exposure experiments, sticking things out there and leaving them for weeks, months, etc., under cosmic radiation, and then bringing them back and trying to look at them. Very few experiments, interestingly enough, have been done on that. There were some done actually on the same virus, T4, by the Russians in the 70s, and they seem to be relatively stable, but very, very little has been done.
There's a bacteria, I cannot avoid
Dinococcus radiovirus.
That has basically a duplicate of every bit of DNA, and it's supposed to be extremely resistant to radiation. And as we get into some really strange possibilities out there.
Yeah, so again, addressing some of these extremely radiation-resistant organisms, we'll avoid the live thing for now. But some of the bacteria that, in fact, were originally isolated from nuclear reactor efflux, Dinococcus radiovirus have multiple copies of their genome and amazing DNA repair mechanisms. And so those seem to be really one of the conditions. Interestingly enough, most of these viruses and their genes are pretty inert. So they don't seem to have that process for being able to actually repair kinds of chemical changes that happen. So, but again, maybe coating it in molybdenum or some lipid, something like that would be really cool. Yeah.
Thank you for your work with coronavirus vaccines.
Yeah.
Appreciate that.
Yeah.
Real
We're still trying to get further with those. And if you know some good pharma companies that are interested in investing, let them know.
Sorry to introduce nasal coronavirus.
Potentially, yeah.
One of the treatments they give after you have this is a thing called Paxlovid.
Mm-hmm. Yes.
And it's called an antiviral, 2 pills of antiviral. Why do you need antiviral? Or what's Paxlovid?
Right, what's Paxlovid? Okay, this is getting back to what Dave was talking about, my 100+ appearances on mostly local media, actually. Got to the point, sorry for a little aside here, but one day in March of 2020, I actually had 5 TV interviews in one day. I said, this is too much. I can't do this. I was on sabbatical at the time, it was convenient, but no, this is too much. So I basically cut back and started doing the local stuff. So this is not my area of expertise by any stretch of the imagination, but I have been teaching virology for almost 20 years. So the antivirals, and Paxlovid is actually 2 different ones. One of which is about how the virus makes more of itself. Actually, 2 different ways the virus makes more of itself. So if you think about a virus, it's basically a bag with genetic material on the inside. And so the bag is all protein, mostly, and again, we can details on that. But the way those proteins are made, they have to be made in a specific way, and they have to get chopped up into smaller pieces, particularly true for coronaviruses. There's something called a protease that does that. And one of the drugs in Paxlovid actually blocks that protease. So if you don't chop up what's called a polyprotein, the original piece that's made, you don't make proper structures. Again, they don't look like this, but the structure that I showed you of SARS-CoV-2 before. But interestingly enough, there's also a second drug in there in Paxlovid, which is now involved in blocking the polymerase, which makes more of the copies of the genome, so the genetic material, then the virus needs to make more of itself. So it's kind of a double whammy in terms of Paxlovid and what it's trying to do in that process. And so the idea there is that prediction of them. I managed to avoid COVID until about a month ago, which was really nice, but then now most of my family did, so some actually got accident. I couldn't because some of the other drugs that I was taking got some monoclonal antibiotics, which is really cool, and so that's another side here. But when I went to OHSU and the nurses who gave it to me, they said, "Oh, you know something about these things? Can you tell us more about the clinical data on this?" I shouldn't say so much. But yeah, the idea with that is, the Paxlovid is that, and a lot of these, the mutant forms, the variants of SARS-CoV-2, the vaccines are not protecting as well against. So the new boosters, something for everybody to be thinking about. Those are hopefully protecting better, but the antibody response that you're getting is not going to be as good, and so that's why Paxlovid has been something which people are using. And hats off to the pharma industry. I have some issues with some of the pharma industry because they're not funding us, but and other reasons too. But the development of some of these, antivirals, and but basically the idea is, in terms of Paxlovid, why have it is because these things can be avoiding the vaccine protection, and so just keeping the amount low seems to be good. And again, that's what Paxlovid is doing. It's blocking the protease from making a shell and blocking the genome from making more genome. So it's a very long answer, but yeah, Dave.
So this silicon coating that you put on viruses, is that really very much like glass? Is it silicon dioxide polymer?
So yeah, again, great question. I'll repeat it again. Usually try to also to again, for the students back there, repeat the question, gives you more time to answer it. And secondly, if people are recording it, actually, you get a chance to hear that. So what is the coating? Is, I guess, another way of thinking about it. Is it really glass? And the answer is, yeah, basically it is. So what I didn't show you at those very early experiments we did before, and then the electron microscopy, that was a EDAX method, which is just looking at elemental analysis, but we also did some X-ray diffraction and looked at the crystallinity, and it's almost all amorphous. So it's really an amorphous silicon.
So how does that dissolve inside an animal?
How does amorphous silicon dissolve inside an animal?
I mean, glass doesn't dissolve.
Yeah, so probably what it is, and there's, as you know, there's multiple different kinds of glasses and where they stand. So what we're seeing, at least in those kinds of, in those first experiments with the X-ray diffractions, opal CT, opal A, I don't know, if, I'm getting into the weeds here a little bit. But we think is what's happening is that that's something which can still dissolve, and the more you go through the process of maturation, if you want to call it that, then probably becomes less and less something which can dissolve. But at least in these cases, it does seem to be coming off, and this is much more of a empirical result. We see it, it's there, but how it's happening? Great question. I think we don't really have a good answer to that yet. And some of the people we're talking to say, we don't give us an answer to that. First, Ken.
And now for something. To follow up on Dave's question and comment, have you discussed or been in consultation with folks in the semiconductor wafer polishing business? Because where does that come from? So the colloidal silica, it sounds like you're taking metasilicate, precipitating on the virus or virus. And this sounds very familiar to the formation of colloidal silica used for polishing wafers in the semiconductor industry, which is a huge volume, low-cost applications. And how it's not exactly glass because it is amorphous. Similarly, in the polishing process, they have really optimized all the variables for establishing size distributions, coding frequencies, and so forth. What have you learned?
So, the question again, to repeat it, is silica is not new to anybody, particularly in the semiconductor industry. And there's a lot of knowledge in terms of silica chemistry, particularly at certain companies in this area, which will remain nameless. We have reached out to some of those people, but have not really gotten too far into that. But it's definitely something Unfortunately, that particular company, which will remain nameless, can pay a heck of a lot more than a startup can. But yeah, we're definitely, we know that there is expertise in silica chemistry in the area. And that's definitely something that we are looking into, but we have not specifically gone there yet. Yeah.
So this is kind of like half related to Dave's question. Have you been able to demonstrate that, especially with the application of many spray for like these silicated, silated,
Silicified, we call it.
Silicified, yeah, okay, sorry.
Only took me about 2 years to figure out how to say that.
Yeah, silicilated. Have you demonstrated that, because silicates are pretty hazardous when actually found in your lung tissue? Is that not, additionally, we have demonstrated that they're even passing the bloodstream. This is something that we just know is kind of a given. It's not,
Okay.
Where's the question?
So, question again, I'm going to paraphrase here, is are you concerned, particularly for some of the nasal vaccines, that you can get silicosis, which is the classic problem, is what a lot of minors end up with, etc. So it turns out that that's very different, and a lot of the problems actually there don't have to actually do with the silica, it has to do with the crystalline state of the silica, and almost all of it's quartz, and these little tiny quartz crystals. So it actually is a physical issue, much more so the shards rather than its actual chemical issue. And again, given that Dr. J is, again, an anesthesiologist, does a lot of pharmacokinetics, and so he looked into this, the amount of silica, which is even in an intranasal injection, is extremely low compared to what you would get even at a chemical basis for a potential silicosis. But one of the questions we keep getting asked is, what's the pharmacokinetics, what happens when you dissolve, presumably that's what's happening, and where does that silica go? Presumably we excrete it in urine, but again, these are a lot of things that we have not yet done.
I have an additional question. You mentioned that there seems to be no sequence similarity, and that it seems like between those structures.
Totally different question.
Very related, separate. That it looks like it was the secondary and tertiary structures that were more similar, but that you mentioned that the primary sequence was not similar. Wouldn't that seem to indicate more convergent evolution on the side? You know what I mean?
Okay, so the question here has to do with an evolutionary question, again, getting way back into why we started getting this in the first place. Right, so icosahedral symmetry, and as I mentioned before, it's just simple geometry, math is math, and so, largest volume for smallest surface area. So that definitely makes sense. But we do know there are multiple ways to, quote unquote, skin the cat. So there are other ways of making icosahedrally symmetric structures, and there are quite a few of them. The fact that we're seeing basically an identical tertiary structure, not even so much the secondary, but an identical tertiary structure, leads us to believe that that's the case. And another reason not to think about it being convergence is it's 3 different groups. For just 2, then I would say, convergence or horizontal gene transfer seems more likely. But again, this is all hypothetical. We don't really know. But there are different ways to make icosahedral symmetric structures. And the fact that you have 3 completely different lineages from each other leads us to believe that it's a common ancestor. And, sorry for a quick aside here, tooting our own horn, there was a commentary that was written to that PNAS article where we were compared to Darwin. It's like, I can just die now as a biologist, I'm compared to Darwin. That's just it. We're done. So,
So following on Ken's for a moment, he suggests semiconductor, I'll suggest something else. People making chromatography media, a lot of similarities. The other question is, in your materials that you're producing, how much residual metals? I'm assuming you're using something like sodium carbonate, sodium hydroxide as a base to start these reactions. And that, of course, leads to the next part is if you have enough of those dangling, then you have a situation where it's locally basic, at which point silica is actually very easy to to attack. One of the most common ways of dissolving glass is you take caustic soda and pour it in, and it will visibly, even in a short period of time, sort of dissolving the glass away. So.
Yeah, so I guess the question here is a little bit about, how are we doing the processes and what things are we adding the analysis for all the extra components that go into the process. At this point, we've done very little extra analysis of these. We actually do an acid catalyzed with a base catalyzed process, and both would work in terms of hydrolysis here. But going in and now doing the analysis of all the other things. One thing we do have to do when we're doing the precipitation process is we do everything in plastic, not in glass, because you will start etching actually in glass in that process. So that's one of the secret sauce kinds of things that you have to do in that process.
I may have a very simplistic question, and I apologize if it's what it is. Now, first for fun, you've been speaking in class, so that brings in vitro in minds. No, let's go back to the class. You're concerned about how the coating, the de-silicon, oh boy, that's not the word for that.
Desilication.
Okay. Would it be at all profitable, intelligence-wise, to use liver cell lines, various types of organisms, lung, liver, the garbage dump of all sites, and find out possibly how the silica is being moved?
Yeah, so the question is basically, where's the silica go? I can paraphrase here. And the answer is, we don't know. We predict it would be kidneys and that process.
And can we test it in empirical evidence
for that process? Now, to be perfectly honest, I'm not anybody who does pharmacokinetics. If you know someone who does, be reasonably interested in working with us, I love to chat. But at least the prediction is it would again be going through kidneys and then being excreted in the urine. How you would test that, being an old school kind of chemist, I would say radioactive silica or silicone would be the perfect way to do those kinds of tests, because you see what the radioactivity is. But whether you can do those kinds of experiments these days, I don't know. So, but I'm sure there are some clever people doing pharmacokinetics who could figure out how to do that. But again, this is based on other people's work on the literature. Should be going through the kidney into the regular nephrotic process. One of the things that we do see, and this is a bit of an aside here, is that we do silica treatment of some of the viruses, and a lot of people are interested in viruses not so much for vaccines, but also for gene therapy purposes. Almost all of those end up going to the liver, like we were talking about. Interestingly enough, when you do silica coating of the viruses, they don't go to the liver. And quite why that is not entirely clear, at least not to me. So this may actually turn out to be a really nice way of detoxifying potentially. And another thing you get, again, I didn't mention this, but when you have a silica coating around the outside, one of the things that happens with vaccines is you make antibodies, right? Antibodies will recognize some kind of antigen, and they'll interact with it, will take it off, and the T cells will do their thing, and then blast them apart. Well, if you happen to have a silica coating around all of your antigens, antibodies can't see it anymore. And so at that point, you may actually have a mechanism to be able to now do treatments that you otherwise couldn't do because everything's got the toxicity going to the liver. Now that's all hand-waving at this point. But it's certainly something that we're thinking about. And other people know it, so it's not disclosing. You should all go off the right paths about. But yeah, so it's a really interesting question. I think we eventually we're definitely need to know where the silica is going, dissolution-wise, and again, the only thing I can think of again is radioactive silicon and where is it coming out of the urine or not. But I'm sure there are other ways of doing that too.
Alternative to radioactive, silica does have an NMR sensitive species. So you could potentially
NMR to detect the differences again in your secretion.
All cell lines, what have you, it shouldn't be particularly common. I lost just with
But particularly things like teeth, vinegar, silk, might actually act as a substitute for phosphate.
Yeah, so one real quick thing about teeth, sorry to sure most of the question there, but I'm getting back to the toxicity issue. One of the things about silica is that it's what's called generally regarded as safe by the FDA for ingestion. All of you hopefully brushed your teeth this morning.
Yeah.
There are silica particles in that toothpaste. 99+% of toothpaste has silica particles in it. And so, for ingestion, it's no problem. And there are also oral vaccines. So maybe you could use that for oral vaccine.
So you're telling us we can eat those silica packets that we get?
Yeah, they seem not to eat them. The problem with that is it's hygroscopic, so what they do is they end up blowing up. So it's not that they're necessarily toxic, but if you start getting these really large silica particles in your gut, I wouldn't recommend it.
So basically, the whole thing you're going to do is now they have to be frozen to like 40 below or something like that.
Well, there's COVID vaccine.
Yeah. So if you can do this, then more people around the world can get the vaccines.
Yeah. So the point here is, and sorry to paraphrase here, but I'm sure a lot of you have heard use it or lose it, and then all these things about the poor people who are out on the freeway, they just come back to vaccination clinic, the stuff is as they thought it, they've got to grab people inside the freeway and inject them. Well, certainly for these guys, you can freeze them and thaw them, and they're perfectly happy. So use it and keep using it.
So that's the mRNA vaccine. We have to do the super familiar with this work for mRNA. You're what we identify as more kind of traditional vaccine with translate from mRNA. Is that the biggest sort of vaccine wave of the future?
Yeah, so absolutely wonderful point, very incisive, and all of the pharma companies we're talking to said, have you done it with mRNA? Have you done this with mRNA? Have you done this with mRNA? And mRNA actually is usually mRNA with lipid nanoparticles, so it's a combination of the two. The mRNA was delivered to the lab last Thursday. We got the lipids, I think, on Tuesday. So, check with me in a couple weeks. So, we're excited about it in theory, depending on the lipids, and there's some interesting aspects about the lipids as well. The precipitation should work. The sol gel chemistry should work. What kind of stabilization we get, not entirely clear. But those are definitely experiments which will be done in the next couple of weeks. Absolutely great point. And definitely. For the developing world, however, getting back to your point, is that mRNA vaccines are still very inefficient. They're still pretty expensive to produce, even without the whole cold chain issues.
There's a lot of just old school diseases that
So
the developing world just needs a traditional vaccine.
Right. Or even the adenovirus-based vaccines, because they're much more efficient. The actual dose you use for those is orders of magnitude lower than you have with an mRNA vaccine. So, although I got all the mRNA vaccines, I'm really happy with them, and I think it's totally cool technology. But I think in terms of developing world, I think some of these other vectors may end up being something which is more applicable. And there's a little patent issue, but we won't get into that.
Yeah, I'm still
Moderna is advisory, and what that means for anybody else trying to develop these things. Yeah, exactly.
Money,
Yeah, there was lots of